All right, so this is a presentation about our super interesting recent audit into the NIM mix network that we did at Cure 53. This is joint work. I want to mention my co-authors, Dr. Alexander Perker, Dr. Daniel Bleikenbacher, Luan Herrera, and Dr. Marta Conde. This was very much a joint effort. And I'm very excited to be able to present this audit because we don't often get to talk about audits because they don't get published very often. Generally speaking, audits are done under NDA, and especially the interesting audits where you actually have findings, generally speaking, companies don't want them to be public because they perceive them to be bad PR or embarrassing. And I strongly disagree with this interpretation of public audits, and I'll talk about that at the end of the talk. But with this one, we were really lucky because I feel like all of us gave it our all. We really tried our best to attack this target because it was a very interesting and innovative target, as hopefully you'll see. And we got a really good result, or a set of results that I'll be trying to present today. So what is this super interesting target? What is NIM? So a lot of you may be familiar with VPNs or with onion routing networks such as Tor, largely intended. These are technologies that are largely intended for anonymity, privacy online. And so NIM is a mixed network, which is kind of high level similar to onion routing, which is the technology used by Tor, but different. And many researchers would argue better in some ways. And so aside from being a practical deployed mixed network, which is rare to see in real world situations, NIM is also implementing a bunch of innovations, largely by incentivizing volunteer nodes to provide bandwidth, by making it such that if you run a NIM node and you provide bandwidth to the network, similar to how Tor nodes provide bandwidth to the Tor network, you end up mining NIM coin or mining some cryptocurrency. I'm not really sure if it's called, I don't think it's actually called NIM coin, but you basically mine a cryptocurrency, and the mining happens through you being part of the network and facilitating bandwidth on the network. And so this is really innovative, in my personal opinion, because it incentivizes people to join the network. This is a problem that Tor has, for example, where, as far as I understand, and again, this is personal opinion, they more rely on sort of like ideological motivation or people wanting to volunteer and be part of a network that's perceived as contributing to the public welfare. Whereas here, you're literally getting cryptocurrency for being part of the network. And there's a NIM blockchain that validates this cryptocurrency custody. There's the architecture of NIM is actually quite sophisticated. There are gateway nodes, there are the volunteer mix nodes, a set of validators that operate similarly to how cryptocurrency blockchain validators operate in other blockchain networks such as Penumbra and so on. And so the idea is that this is like, it uses an innovative mixed network system to give access to easy to use anonymity to end users, but also it allows incentivization of mixed nodes by making it such that if you participate in the network, you're also mining tokens, NIM coins or cryptocurrency. And then I suppose this currency is redeemable against other cryptocurrencies in some way or another. I'm not sure. So our audit of NIM was mandated actually a while ago in July 2024. And it covered the NIM mobile apps, the desktop apps, the VPN infrastructure, the backend, the cryptography libraries. It was a very far-reaching audit. More or less covered, I believe that we covered everything that's relevant. Maybe some things were not covered, but we certainly had a very large target to deal with. And so this audit lasted weeks and weeks, and the entire team that we had, a large number of experts. Certainly, we were busy for a long period of time on this audit. So we had, I think that my team and myself, we're very proud of the result that came out of this audit. We're also very grateful for NIM that were allowed to talk about it because that was their decision. And again, I'll talk more about how companies make or maybe should make these decisions, in my opinion, at the end of this talk. But we have 43 findings as part of this audit, and not all of them will be in this talk, but you can access the full report at the URL at the bottom of this slide. And basically, this talk will be a top 10. So I've selected 10 issues that I hope are the 10 most relevant issues, and I'll try to explain why they're interesting and what they say about the state of state-of-the-art, novel, R&D, cutting-edge R&D cryptography software in 2025. So let us begin. This is an interesting one. So NIM uses an innovative anonymous credentials scheme called, it can be used for anonymous credentials, but it's also usable for other things, called Coconut. And so strictly speaking, it's a distributed cryptographic signing scheme. But we found that validation on inputs to this to one of the underlying signature schemes was not done within the library itself. And so in each of these findings, you'll see on the bottom right, I'm providing what NIM is arguing, is what NIM's response is essentially to the findings that we have. And their response to this one is that they do actually verify inputs to the BLS12-381 scheme upstream in the code base. And so while it affects the Coconut library, it never affected the stack from the perspective of the end user. So our response to this is that the stack is public, like the Coconut implementation is published as a Rust crate that's supposed to function on its own. And we asked whether NIM was interested in reusable code, and their answer was yes, and they're very much interested in making their code reusable and secure. And so they're validating their inputs to ensure that you don't have things like infinity points and other invalid inputs. So validating inputs on asymmetric schemes of all kinds is something that cryptographers talk about a lot, and auditors see a lot in implementations. And often in the context of elliptic curve implementations, you end up with things like invalid curve attacks or small subgroup attacks, which plague curve 25519 or ED25519 implementations. And here we had something similar in a sense where a lack of input validation could lead to unexpected behavior on an asymmetric primitive. And this will pop up again a few times. So this is another totally different issue. NIM uses something called offline eCash, which is a way to basically give people tickets, I guess, is a good way to explain it. So these are redeemable tickets that are cryptographically issued and then can be redeemed at another vendor. So like one vendor that's connected to the NIM network issues those tickets, and another vendor will redeem those tickets. And they maintain their validity across the network. So in order to generate a unique identifier for each ticket, the NIM will just hash the pay info, which is supposed to be a unique string. So this pay info is supposed to contain a bunch of things regarding the essentially a description of the payment and sort of like the context of the offline eCash ticket. And this includes vendor ID and so on. However, it was all concatenated together, which leads to a situation where you can have a collision. So you can have a pay info sort of description where the vendor name and the ticket name when concatenated, match another vendor name and ticket name. And so the right way to do this, this is something that's known in cryptography and applied cryptography as context separation. You want to use a keyed hash function that is designed for these sorts of purposes. And so we recommended that you use HKDF, and you separate the vendor ID, and HKDF has fields for these sorts of inputs, and you can use the info field and the salt field in order to then generate a hash that is indeed context independent and that avoids collisions. And so NIM, in their response, acknowledged this issue and will address it in future releases. I think they might have addressed it already. So we again had a partial signature bypass also in offline eCash. Again, this was an issue with a lack of validation. And again, it's extremely similar to the first one, but the consequences were quite severe if you use the eCash library on its own. According to NIM, they do implement verifications upstream in the code base. We were not able to verify this within the context of our audit, but they showed us that they do this afterwards. And so while it does affect the offline eCash library, NIM claims that this does not affect the rest of their stack. And so again, this really showcases, like, when you have these cryptographic systems that are cutting edge, coming straight out of the lab, a lot of them tend to use a bunch of novel elliptic curve-based asymmetric schemes, whether it be for key agreement, for signing, for threshold cryptography, all kinds of things, MPC, who knows? And so all of this stuff really depends on input validation. Input validation continues to be very important, and skipping it leads you to the same attacks that we've seen on classical, X25519 systems for probably more than a decade now. And this sort of attack continues to be relevant here today. We also found, speaking of classic attacks, this is certainly a very, very, very classic attack. I remember myself making this mistake very early on in my career as a open source cryptography software engineer. AES, the standard block cipher, has a bunch of block cipher modes. And if you use AES encounter mode, you need to make sure that you never reuse the same nonce with the same key. Because if you do twice, then XORing the two ciphertexts will give you an XOR of both plaintexts. And in NIM gateways, we discovered that all encryption was being done with AES encounter mode with a fixed IV of 0. And there was essentially no key rotation, probably no key rotation at all, if I recall correctly. And so you had tons of encryptions that were happening under the same key, and the nonce was being reused all the time. And so this was definitely quite a serious finding that could lead to a lot of plaintext recovery. Because if you just take two ciphertexts and XOR them together, you are gaining a lot of information on the plaintext. And effectively, of course, the fix here is to not use fixed nonces, to rotate the keys, and especially to switch to a better AES mode, such as AES-GCM SIV, which also provides authentication, integrity. It's an authenticated encryption mode with added data, and also protects against, has a certain level of protection against nonce misuse. And so NIM's response is that they are fixing the issue and upgrading to AES-GCM SIV as recommended. Okay, this one's really interesting. So, Bloom filters, so before I explain Bloom filters, so NIM credentials are supposed to have serial numbers that prevent misuse. So if you have a NIM credential and you're like sort of using it like a one-time credential ticket that gives you access to the NIM mix network, you're gonna want to use that credential to authenticate yourself to a gateway, right? But the gateway needs to keep track of all the credential serial numbers or whatever that are being used to access the NIM network. And so the naive way to keep track would be to just have a database somewhere and it has all the credentials, right? But that doesn't scale. It scales linearly. It's you don't really have a plan for what's going to happen when it's been 10 years that the NIM network is running and you have 1 billion credentials and you can't really delete credentials because that means that they might be reusable. And so NIM uses an approach called a Bloom filter. And so a Bloom filter is basically a bit array that's a specified size, and you can determine how big the size is of this bit array. And the bigger it is, the more resistant the Bloom filter is, as we'll see, to false positive situations, to giving you a false positive. But basically what a Bloom filter does is that you give it a value, it stores it in the Bloom filter, and then when you give it that value again, you can query the Bloom filter to ask, hey, has this value been stored here before? And the Bloom filter has only two possible answers. It'll either say probably yes, with some degree of probability, which you can control, or definitely not. So it will, if a Bloom filter returns no, then absolutely it has never seen that value before. And if it returns yes, there is a significant probability that you can configure that, yes, this value has been stored before. So a Bloom filter is a constant size data structure. It scales much better than a database, but you really have to make sure that you configure it such that there aren't false positives. And this depends on a bunch of parameters that you have to set. So the parameters that were set in the NIM gateway code base that we audited, K equals 13, M equals 250,000, meant that after only 2,000 NIM users, and we came to that estimation by estimating how often a NIM user would need to use a ticket to authenticate to a gateway, and so on. Basically, 2,000 NIM users would lead to roughly 40,000 entries. And if a gateway were to handle more than just 2,000 NIM users, the Bloom filter would end up with a false positive rate of 1 in 6, which could cause a denial of service situation. So NIM had a response to this, which was that this was test code. They always planned to fix this before it hit production. And also they were interested in migrating to binary fuse filters, which we recommended. So binary fuse filters are a data structure that's quite similar to Bloom filters, but their false positive rate is smaller. So it's a computational improvement on Bloom filters, and so it's just a better data structure. It does basically the same thing. But yeah, like Bloom filters are a really interesting data structure. They've seen a lot of research. Binary fuse filters are relatively recent, in fact, and came after cuckoo filters, which were another incremental improvement on Bloom filters. But you need to make sure that you specify the parameters correctly. And of course, increasing those parameters means that you will, so increasing the hash function parameter, which is K, will lead to a performance hit, and increasing the size of the Bloom filter will lead, of course, to a size hit. So you want to make sure that you balance these according to your needs. But of course, anything virtually that you choose here would almost certainly still be better than the classical solution of just storing all the credentials in a database, right? Because that really doesn't scale. You can't delete them. It's a nightmare. Yeah, this was a really interesting finding. Once again, we had a situation where this isn't exactly input validation, but more so that there is a usage of the Pointcheval-Sanders signature scheme again in Coconut, the distributed signature / anonymous credential scheme that's used by NIM. And if you only use public values, you can end up in a situation where you have a H value, which is supposed to be unique for every signing. And it's not unique. You end up with a reuse of a value that is mandated to be unique in order for signature forgery to not be possible. And we found that that was not the case. Again, NIM argued that this depends on how the library, the Coconut library, is integrated against the higher level NIM software. And so they informed us recently that this risk does not apply to the NIM system, since Coconut and offline eCash do not uniquely use public attributes for H as they are configured in deployment. So the bug is still present in the independent library. And again, input validation for signatures, definitely still a big thing. And wouldn't you believe it, so these are all like critical vulnerabilities or vulnerabilities that we labeled as critical. And once again, there was a situation with a signature aggregation function that's supposed to check bilinear pairings, and it again accepts the point at infinity and produces invalid outputs. So the response from NIM is that, once again, there is verification there is input verification upstream in their code base. And so again, that really depends on how the stuff is used. But within the context of the actual libraries, this is not something that we were able to verify within the scope of the audit. One other thing that we found was that NIM, so you've probably seen this in the VPN that you've used. If you download some VPN, like a standard VPN, not a mixed network or anything like that, like Mulvad or whatever, it'll try to connect you to the fastest node. And so sometimes this could be the node in your own country or in a neighboring country. It'll do maybe a bunch of latency checks or speed tests and determine what's the best node for you. So in the case of the NIM desktop app, NymVPN desktop app that we audited, we found that those nodes were hard-coded. So it was always either France or Germany, and no other country was ever considered, and there were no tests that were made. And so this is bad for obvious reasons. It affects traffic distribution, may negatively impact the anonymity set. And so obviously you want to implement, not only do you want to implement dynamic real-time systems for determining the fastest nodes, but also in the context of an anonymity network, which is a set of security guarantees that are far superior to the security guarantees that are targeted by VPNs, classical VPNs, whether they admit it or not. You want to make sure that you can do that without affecting the uniform distribution of the anonymity set. And so that's a unique challenge. However, NIM says that this bug has also been fixed, that it was only true for development builds that were shared with us, and that, which were the ones that we audited, but that those that hit production did not have this. It was fixed before it hit production. So that's what we got. And finally, I think this is the last one. We also found that credentials and key material are insecurely stored on iOS. So in iOS, you have this API called Keychain, which has existed for lots of years. And it's also, it offers a stronger set of security guarantees on iOS than it does on Android, because to some limited extent, iOS is able to use hardware-backed security when dealing with keychain storage and fetching. And so when you set, for example, a property such as after first unlock this device only, it means that you're invoking Touch ID or Face ID, which are hardware-backed mechanisms to ensure additional security against the unauthorized retrieval of private keys. However, this was not used by the NymVPN app, and so we were able to just dump private keys off the device, no problem, simply by connecting it to a computer and doing a simple file dump. So again, Android has the Android key store, iOS has the iOS keychain. These are security mechanisms with differing level of effective security, of course, depending on the device type and use case, but they do offer some way to limit access to private keys, which continues to be like ever since we had to store PGP keys or SSH keys on our desktop or laptop computers, this has been a problem. And it continues to be a problem, even in the mobile space sometimes. And even with cutting edge technology, we still have asymmetric cryptography. We still have the need to store those keys in a way that makes sense and takes advantage to the best degree possible of hardware-backed security guarantees. And this continues to be the case whether it's a mixed network or a cryptocurrency wallet. Certainly you can ask questions regarding whether a browser plugin is the best place to store your cryptocurrency private keys, but that's a different audit, and it continues to be relevant here. So again, I want to go back to what I stated at the beginning of the talk. We do audits like this a lot, and this is certainly not the only audit last year where we found a bunch of bugs that were significantly serious bugs that could lead to a huge bypass and some, depending on context, depending on deployment, depending on the code that reaches the user, etc., but could have a significant impact. However, this is the only time that we, so far at least, that we were able to actually go and talk about our findings. And so why is that? Well, the perception is that if you mandate an audit, well, from a company's perspective, you're mandating the audit, and this is maybe a bit pessimistic, but maybe the board asked you for one, maybe the investors want one, maybe there's some bureaucratic hurdle that is some governance issue or some regulation issue or something like that. Some business partner wants you to get an audit. So you get an audit against your will. And then as a business, you want that audit to be spotless. And if it's not, you get angry. And if you're angry, what you want to do is either basically argue with the auditors, which happens, or try to just ask for it not to be published, which of course is, you're right. We can't publish, and we don't publish audits unless we have permission from the client, and we assume that the client does not want audits to be published. But my point is that this is a defensive, business-minded mindset, and that in reality, when you conduct an audit like that and you have a bunch of findings, and especially when these findings concern cutting-edge, innovative technologies, what the public should get out of audits like that, and what researchers, in my view, absolutely get out of audits like that, is that this is a serious company. And this is a company that's committed to transparency, committed to producing actual high-quality code in reusable components written in Rust that the broader public can use, especially in relationship to new technologies, anonymous credentials, distributed signing, threshold offline eCash, issuance, stuff like that. This is all what we call like fancy cryptography, essentially. Not a lot of libraries exist that can do stuff like this. And so when a company actually invests the R&D, makes their code not only open source, but reusable, and in spite of course, there's going to be bugs. This is research. This is just hitting, the general public, mixed networks that work like that are this sophisticated are rare to non-existent. And so when you have a technology, a sophisticated novel technology like this, of course you're going to have findings. But fixing those findings from a strong audit that actually manages to point them all out and lay them out and issue recommendations that are solid recommendation and verify the fixes, which is a lot of work, is how products actually mature from PhD student, lab, whatever, R&D to consumer grade technology. And this is why, like, I'm not here to just praise Nim, right? But I really think that this is important. I want to use this opportunity to make a point. I think that it would be to the benefit of everyone if companies looked at audits as a way to solidify their credibility, even if the audit has significant findings. Because if you're not publishing the audits, that's not, that's only informing the least informed and the least engaged of your users that, hey, it's probably secure. But you're going to have those bugs anyway. And once you have those bugs, once you have them in an embarrassing way that hits the media, a lot of people are going to ask whether you did due diligence, and due diligence in that context means an audit. And so in this case, you have a situation where you had a company that was committed to transparency, committed to actually having an actual independent, hard-eyed, critical look at their technology, committed to transparently publishing the findings so that people can learn from them and that people can understand the state of the technology as it evolves, and of course, fixing them. And I've been in this space for 7 or 8 years. Again, I'm not speaking on behalf of Cure 53, of course, I'm speaking on behalf of my personal opinion. But I really think that a lot of companies, a lot of the entire space could stand to gain from the example being set by clients like Nim that are that transparent. And so we were able to quickly work with them on addressing virtually all the issues, certainly all the critical ones, maybe some of the lower severity ones that you can see if you read the full report. Again, I only covered 10 issues. Reminder, the report is 43 issues. Some of them are lower severity, maybe they'll be covered later. But if you're going to have more cryptography, you're going to have more cutting edge cryptography, you should definitely expect to have more and more bugs. Some bugs may mirror the classes of bugs or types of bugs that we found 5 or 6 years ago or a decade ago, but some of them will be novel and some of them will be both novel and classical, even if you're using a new kind of signature scheme or anonymous credential scheme and all that fancy stuff that's keeping a lot of applied cryptography people in the blockchain space and anonymity space and secure messaging space and so on busy right now. Okay. So again, I want to reiterate, this was a joint effort with my colleagues, Alex Perker, Daniel Blakenbacher, Marta Conde, and others. And you can download the full audit report at this link at the bottom of this slide. I encourage you to check it out. And that was my talk. I'm going to stop sharing my screen now. And I think there might be some questions.